Oh, right. So I just wanted to go through a couple of things that I skimmed over a little bit in the video to do with the technicalities and some of the more scientific sides of discovery. Um, so I thought I'd start with the design of the probe itself and some of the instruments that it brought along. Um, there was a lot that they managed to stuff onto this thing, even at almost 6 tons. It was pretty grand. Um, the dominating sort of features of the Cassini spacecraft already, it had an 11-meter long magnetometer boom, and basically this acted like a giant compass. It had two magnetometers actually in it, one that was specialized and designed to look for the magnitude of the B field, and there was another one which was a vector magnetometer, meaning that it also gave direction, and then it could sort of confirm the magnitude, but not to quite as much accuracy. For the most part, mapping out the outer reaches of the magnetic field of Saturn, you'd be dealing with fairly weak fields. At the surface of Saturn at the equator, I think the field is about half. Was it half a Gauss? I think it was about that. So um, I don't think it's terribly far off of what Earth's was. It's just Saturn being larger means that the field extends a lot farther. Um, it had two electric field antennae. These are probably visible in a lot of other um, images of the spacecraft, and those were, again, they kind of stand out a little bit. Um, the high gain antenna, this was designed to pretty much be facing back at Earth or to other probes in the Deep Space Network, most of which were still in the inner solar system, um, as much as possible. Pretty much any time that they would have to turn Cassini away to take images, it would then have basically programming to turn back towards Earth as soon as it could, and then relay everything using that antenna. And if it ever found that it couldn't contact Earth for some reason, the probe would automatically reorient itself, um, so that it could try and get back in contact. Sometimes it would lose contact momentarily as Cassini went behind Saturn or went behind some of the moons. And at that point, there's just no way to contact the probe. You have to wait until it comes out the other side, right? So just one of the nuances of space flight. Um, there were a whole host of other sensors here. So this remote sensing palette was mostly a base for a number of cameras. There was one visible camera and two infrared, is my understanding. Up here, it isn't labeled, but this is a Doppler radar that was used for surface imaging, especially of Titan, because, I mean, you can't really get very good surface images in the visible or infrared. So the Doppler component of this means that Cassini could actually point this radar at a moon, and, well, it would already know its speed from other means, but if there were, sharp elevation changes, or if there were sharp features, then a sudden increase in the frequency of light coming back to the radar would actually indicate that there was a sharp bump in the surface or something like that. And so that would this would sort of help with surface imaging. Let's see. Yeah, so the three RTGs, they're around the bottom here. The other one's on the far side. So, like I mentioned in the main video, these use plutonium-238. The engines were about 500 newtons each, but thrust really isn't a very important feature in space because you have all the time in the world to change your speed. It's about how efficiently you can do it. And then the final thing on the back here is Huygens itself. So this is before it was released, and it was sort of strapped onto the side like this. Huygens, for sort of size reference, is about the size of like a large coffee table. It's like a meter across. The heat shield here is a little bit bigger, but Huygens, as I'll talk about in a little bit, it had a really, really steep sort of it came into Titan's atmosphere really steeply. And so it really needed quite a heat shield to take that, but because it was all electronics, there's no risk of uh, killing any crew by having too high of a G load. So the next image here, this is temperature data taken by Huygens on its way into Titan's atmosphere. A lot of the science that Huygens did, the majority of it even, was done on its way down, and they knew that it was going to take a little while. But this kind of shows what Huygens found with temperatures. So using the same divides that we do here on Earth, thermosphere, mesosphere, stratosphere, and troposphere, you can see all the same inversions. It's a little bit more drawn out here, and I guess you could argue a bit as to where the mesosphere actually is, because there's not a whole lot of like the mesopause here, where the temperature just kind of stops, is actually quite large. You see it goes over like 200 kilometers in altitude. This other line on the chart, though, this is the vertical resolution, and this actually has to do with how fast Huygens was traveling. So Huygens, like I said, it came in at a very steep angle. It was about 30 degrees relative to the surface. And this meant that coming from, very high speeds on the order of, I think, about 8 or 9 kilometers per second, it came down and slowed right down. This actually reflects pretty well logarithmically what its speed was, because it was only taking measurements every so far. So it was enough to determine this temperature gradient, but you see the speed of Huygens was pretty much constant, and then in comparison, I think the ISS orbits at about 500 kilometers above the Earth's surface, so about here is where the ISS would be, and Huygens just slowed down really quickly. And that's when the resolution increases, because it's now moving slower. And these wobbles further down in the graph, this is, I believe, due to high winds in Titan's stratosphere. There was almost no wind at the surface, but at parts of the descent in the upper atmosphere here, Huygens would actually be moving faster sideways than it was down. But yeah, so there's one more quick inversion in the temperature gradient here, and this is right down only 10, 20 kilometers above the surface is where the troposphere starts. And then the surface temperature was about negative 180 Celsius, so 90 Kelvin. This is a radar image that's been given color just for contrast. That was taken over a number of flybys by Cassini. So Titan's North Pole here, and they thought that there was going to be possibly liquid all over the planet, but because they basically didn't know well enough what the temperature and what the surface conditions were on Titan, they didn't quite have that right. But here at the North Pole, it's a little bit cooler year-round. It's already insanely cold in Titan, but here we've got these hydrocarbon lakes, and these were very easy to tell what they were without any like spectroscopy or anything. This is just a radar image. So basically, if you're shining a radar onto a surface like this, and you find something that's suddenly smooth and glassy, there's barely any wind at the surface of Titan. So this was just completely glassy, and you could then immediately tell, like, well, that has to be liquid. It's shaping itself nicely like that. Yeah, so even though there wasn't hydrocarbon lakes or oceans even over the rest of the moon, there was still a fair bit of it here. So the surface of Titan, that Huygens saw, there were a couple of noteworthy features. So there was no ocean, obviously. It sat in soil, and I think Titan was found to be about sort of half water ice and half mucky grit. That was fairly similar to, I think, places like Mars. But there were some noteworthy features on the surface that came sort of before that, under, maybe not soil, but the dirt underneath. On the top, you see all these rolling pebbles. These are actually made out of water ice. Um, so it's almost like large particles of dew that have, frozen. Um, the light in this image has also been greatly, greatly enhanced. You already have 100th of the light that you get at Earth, or the photon flux here at Titan, but you're also under those clouds. So the amount of light that you had here, even at the brightest part of the day, was about the same as nautical twilight on Earth. Um, but again, like that's nautical twilight looking down at the ground, not looking up at the last light of the sky. Um, so this was actually really dark. You wouldn't really be able to see here. This is just a fairly long exposure that Huygens made. You'll also notice that all these stones are rounded off. Um, they're not very big. Again, like Huygens, about the size of a coffee table. This would be, you could probably carry this rock on Earth. Um, but you see, they're all rounded off, and this was a pretty solid indicator that there had been flowing, um, liquid of some kind on the surface fairly recently. Um, It was also found that the soil that Huygens bedded into, it did sort of collapse into the surface and make a little hole, even though it didn't come down very hard. So the surface was quite, you know, weak, if you will. But the soil underneath, Huygens cooled down really quickly after impact, and that actually made people think, and I think there were some calculations to actually show that this was the case, that the soil underneath would have to be very wet for heat to leave Huygens as fast as it did. So, whole bunch of indicators that there's still things to do with liquid going on here. This is an image taken side-on of Titan's atmosphere by Cassini. Titan's atmosphere is about 95% diatomic nitrogen, and a lot of that just hugs the surface and gives you this haze. But through all the temperature inversions, you get a bunch of funny stuff going on, because then there's also about 5% methane, which we did our assignment on, and found the rate at which it's being destroyed. And then you also have about 0.01% of the atmosphere by number is hydrogen, which isn't going away, mostly because of Saturn's magnetic field. Titan does not have an active core; it does not have a magnetic field of its own. But it's also been able to hold on to a little bit of hydrogen over time. So, moving on to Enceladus. So, of course, this isn't something I can find an actual image of, and there weren't a whole lot of charts, but I thought I'd just look at this and discuss it anyway. So basically, Enceladus is one of the closer moons to Saturn, and like with a lot of the Galilean moons, what was found is that it seems to have a liquid ocean underneath an icy surface before a rocky core. And there's more direct evidence of this at Enceladus than at a lot of the Galilean moons, because we're just kind of inferring it from other things there, but we can actually see evidence of it, literally spitting out of the ground at Enceladus. So you've got these fissures, and what's going on here? It's thought that there's it's sort of a two-pronged process, because you've got the blanket of ice, but Enceladus is also very close to Saturn, and it's tidal heating causes basically underwater volcanoes to form. It's kind of not unlike Io in that it's close to Jupiter, and then it's got the volcanoes of its own. And the reason that it's got an active interior is basically just that tidal heating, and that's why Io is the most volcanic place in the solar system. So at a smaller level, that's also happening in Enceladus, and it's thought that this creates these underwater thermal vents. And that has the effect, and I think it's a little bit exaggerated here, and that the thickness of the ice in this has actually been exaggerated. There was an updated image of this that had it a lot thinner, but it didn't show the cracks or anything as nicely, so I used this one. Basically, the combination of that making the ice thinner here at the South Pole, and this also kind of being the apex of all the tidal squishing and smooshing and elongating that happens at the sort of the equator of Enceladus here. This causes basically these fissures to form. Enceladus is a pretty small moon. On the whole, it's actually only about the size of the North Sea, or I guess you could compare that a little bit better. Like, it's about Vancouver Island across. It's really not a very big moon. And so this ice isn't quite as thick as it looks. And again, this has been exaggerated. Um, so it allowed a place for this. It's mostly water, but I'll discuss what the rest of this was in a sec. It allows the water and other things to be forced out of here. And what's forcing it out is actually the weight of the ice on the ocean. It's like squeezing a water balloon, or if you haven't tied it off yet, right, all the water squirts out. So that's what's going on here, and it's not actually a very dramatic effect. You can see it quite well here, and in some Cassini images you could as well. But I think the rate of mass loss is on the order of about 500 kilograms per second. It's not a whole lot, considering that it's happening across such a big region and it's creating an entire ring for Saturn. They found a number of things in these plumes, so it was mostly water vapor that was then very quickly ionized by the light from the sun. But there were also simple organics like hydrocarbons and carbon monoxide and dioxide. And this was found by Cassini's mass spectrometer, which is something actually I should go back and explain here. If I head back to the first slide, another instrument that Cassini had, I forgot to mention, there was a pair of them. One was a mass spectrometer, and another was called the cosmic dust analyzer, and they both basically work the same way. The idea is that they could, take these samples of extremely sparse stuff in like the interstellar, or sorry, the interplanetary medium. Take these samples, ionize them, or in some cases they'd already be ionized, and it would fire these like through a magnetic field. And as we know, like the amount that the trajectory of a charged particle is bent in a magnetic field is proportional to the ratio of its mass and charge. And basically this is what the mass spectrometer does, is it figures out how much these trajectories bend, and then the spectrum that it gets isn't a spectrum of wavelength, it's a spectrum of mass to charge ratio. And from that, and the different abundances of different things that are appear in different parts of this mass to charge spectrum, basically you can infer what the sample was that you took, or what the abundances of different things in there are. So I thought that was a really neat thing. And so here at Enceladus, Cassini flew about 30 kilometers above the south pole of Enceladus through these plumes, took these samples and figured out that this is mostly ionized water vapor. And then you've also got trace amounts of hydrocarbons and carbon monoxide and dioxide. And so that's all the images that I've got that I wanted to explain in a little bit more depth. I hope this helps, maybe creates a few more questions.